So anyone who's coming in now, there is a repo that is, if you want to follow along, which I strongly recommend, you go to Snoyman.com, click on this repository link, clone this repo, and then follow the setup instructions to make sure you're able to run the exercises. Cool. Welcome, everyone. Today I'm going to be working through, this is going to be a workshop. This is not going to be a talk. So there's going to be a lot of working on code yourselves, interacting together. I hope not to be talking very much at all, in fact. So get ready to type and use your computers. I'm going to be presenting on software transactional memory, also known as STM. And we're going to be doing it in Haskell. STM, just to get an idea, who here has ever used STM before?
For fun.
For fun, fair enough. Who here feels very comfortable with STM? Good, OK. Cool. Knowledge of STM is not required in order to understand what's going to go on here. So please do clone this repository. If you go to Snoyman.com, my website, you can come to this list of talks, click on this repository, and it will have, you'll get to the right repo. And then inside the README file, there are instructions. You will need to install stack. Yeah. Say again? Apparently not.
That one's just for recording, I think.
Oh, it's only for recording? That's too bad. Is there any way to tie into the audio system? Do I just have to talk louder?
Just get all your anger out by yelling at us. You can also move closer to the speaker.
To the what? To the speaker?
It's not that much.
OK. I'll try to speak up. Yeah, so anyway, in order to do this, we need to have stack installed on the system. Stack is a build tool for Haskell. And if you run this next line, it will install the right version of GHC, the Haskell compiler, and it will build the relevant libraries that you're going to need. So everyone, please get that started now. We'll start off a little bit slowly so that I'll talk about some general stuff, and then we'll be able to hopefully have everyone here with a system that's set up.
Test, test. Not do anything.
No luck? Oh.
So those work.
That's OK. I'll use one of these then.
Can I use this?
Sure. Wait, I turn this on. There we go.
There's some way to turn it on.
Test. Whoa. OK. Everyone can hear me now? OK. Wow. Echo. Echo. OK. So also, when we're talking about prerequisites, you do have to know the basics of Haskell in order to follow along with what's going to go on here. Usage of monads is definitely we're going to be using monads. Let's put it that way. Keep in mind the difference between mutable and immutable variables. That's going to get clear very quickly as we're going through here. And just as an idea, who here has ever dealt with race conditions in any language at all? Nice. OK. So you guys will be able to appreciate what's going on. OK. Format of the workshop. This README is at the root of the repository. You guys can follow along on your own machines. You can listen to me talk. Inside the repository, there is there's an exercises directory. This exercises directory has a bunch of exercises that we're going to go through. If you're a little overwhelmed, don't be. Most of these are really easy. We'll spend somewhere between, on the first few, we'll spend just 1 or 2 minutes. Later exercises, we'll spend somewhere between 5 and 10 minutes. Don't worry if you're not able to complete the exercise. We'll do it all together. And if you really want to nail the material down, do the exercises again afterwards. Anyone who's gone through training with me before knows that this is a mantra. Actually, a mantra thanks to Chris Allen. He's here in here. OK. So let's go ahead and there is a team. Sorry, could you repeat the?
Is there any kind of like communication channel here or Slack or anything for basic questions?
Yeah, there is a support channel right now. Does anyone know what the support channel is called?
It's
IT?
That's something
Photoshop,
that's
Python, IT.
Okay.
I'm also right here. So.
Oh, there you are.
Yeah.
Yes. Chris is the one who taught me that exercises are really, really important. So you can blame him for how crappy this talk is. Okay. So just to make sure everyone's system is set up, I've talked slowly enough. Hopefully everyone's got GHC set up now. Let's go ahead and everyone try to run exercise 0 or complete exercise 0. And I'll show you what that looks like. So inside this directory, I look at these files, /exercise. Oh no, it didn't work. Who would have thought that would happen? No. And then you come in here and we have to try to figure out how to fix it. Can anyone try to help me figure out how to fix this code? Say again? Yeah, that's what I forgot. OK, cool. We do that. We run it, and it works. Yay. Edit the exercise files. Try to play around with them. There is also a solution file in each directory. Try not to cheat. Try to go ahead and try to do these yourselves first. All right. Actual material. Mutable variables. So in Haskell, all variables are immutable by default, or said differently, all variables are immutable. This code doesn't make any sense in Haskell. You can't create a variable x and then add 1 to it and then print it out. Haskell is going to scream at you about the fact that this operator doesn't apply here, blah, blah, blah. It's actually going to say the operator doesn't exist, but you get the idea. Instead, the typical way that we deal with mutable variables in Haskell is we don't. We just create new variables. We refer to the old ones. This is immutability. And instead of adding 1 to x, we would define a new variable y, which is x plus 1. So who here can tell me some kind of a limitation with the fact that we don't have mutable variables in Haskell? We'll pretend we don't have them at all for the moment.
slow code.
Slow code is a possibility. It's a good one. We're not going to talk about that one today. It's fair enough, and, but not our topic. Yeah? Sharing memory between threads. That's the important one for STM. If you want to go ahead and have multiple threads communicate with each other, share information with each other, if you have no ability to mutate variables at all, you can't do it. You can't update, you can't create y in one thread and magically have it appear in the other thread. It doesn't work. So this is a pretty inherent limitation, and if we want to do concurrency in Haskell, we're going to have to overcome it. For our purposes today, that is our goal. Our goal is to be able to do multi-threaded programming in Haskell. Other purposes for mutable variables are not going to be on the table. All right. In order to get started with mutable variables, everyone go ahead and open up exercise 1. Just to get an idea, who here has already completed? OK. Cool. So let's ask the compiler, which is a standard practice in Haskell. Let's ask the compiler where we screwed up. Could a match type ioref of char, or string? List of char is a string with list of char. Who can explain to me what's wrong with this code? Yeah?
Trying to print the reference and not the thing at it.
Trying to print the reference and not the thing that's inside of it. Yes. This is exactly the point that I want to get across about mutable variables in Haskell. Unlike, for example, C or other languages like that, where the variables themselves are mutable, we have this two-step process. You have variables. These variables are pointing to references, like an ioref in this case, and that reference is holding on to something that can be changed. You can't directly print that. For various reasons, including referential transparency, which we're not going to get into too much right now, you have to first extract the value. Who wants to give me some idea about how to extract the value and make this code work?
Line 10.
Yeah.
Say again?
Line 10. Just do what you did on line 10 with the variable.
Like that?
And then print that.
You can actually just call
You can actually, I mean, there is name. Yeah, you can use the same names again.
Oh, okay.
You can, but I actually think it's good practice to use a different name each time.
What you can't do is do parts that are like $read_IO_ref. That will not work, correct?
You mean like that?
Yes.
Correct. You can't do that.
If you just use the reverse bind. Yeah.
Not going to get into reverse bind. You're right, but no. Okay. Cool. So that's an IORef. An IORef is one way of doing mutable variables in Haskell. It's the simplest way. It's kind of the default, but it's not the one we're going to be doing today. The reason for that is because I called this talk STM. I didn't call it IORef. So I got to actually do what I said I was going to do. So an IORef works like a mutable variable in most other languages, in the sense that it's a value, you can read it, you can write it, and not much more beyond that. IORefs are very vulnerable to data races and other kinds of race conditions, just like you would have those kinds of problems in other languages. STM, software transactional memory, helps us avoid a lot of these problems. I'm going to get this out of the way right at the beginning. There's no such thing as a magic bullet that solves all concurrency problems. You can have a concurrency bug in Haskell as well. What we get out of all of this is it's much easier to write correct code in Haskell as a result of STM, if you use it correctly. There are two basic building blocks for STM. Yeah?
When you say it's much easier to write correct code, do you mean it's much easier to find problems?
No, what I mean is it's much easier to not accidentally read an old value and then update it while someone else was changing things behind your back.
Oh, okay.
So the two basic building blocks for STM are the STM type constructor and the TVAR type constructor. STM is a monad, and it provides this monadic interface for being able to sequence actions that are all working on TVARs. The thing about STM is that everything is transactional, which means that all of your actions either happen or don't happen at all. By contrast, with most mutable references in most languages, you could have a few changes and then you throw an exception or something else like that. Those changes still happened. And with STM, as we'll see, a transaction either completely occurs or it doesn't. A TVAR is just like that IORef we saw, except it's in STM. And we'll see how we interact with it. In fact, right here. The read IORF function that we saw before takes an IORF, and it extracts the value as an IO action. Read TVAR does the same thing. It takes a TVAR of A and gives you back an STM action in A. We had write IORef. Now you have write TVAR. Atomically, since all of these things are happening inside STM, at some point we need to actually be able to run this thing. And the way we run our programs in Haskell, everything ultimately comes out to I/O. So atomically, we'll take a block, a transaction, and perform all of the actions at once inside of that transaction. We'll see what that looks like. That part might be a little abstract right now. And then you're able to create these things. So new IORef lives in I/O, new TVAR, and then there's also a helper function, new TVAR I/O, which lives in I/O. If anyone is curious, you could try to implement new TVAR I/O in terms of atomically, for example, atomically and new TVAR. Can anyone take a guess as to why we need a new TVAR I/O instead of just having new TVAR? It's not just for convenience, believe it or not. Hold on to the thought. We'll come back to it later.
Does it automatically execute?
It does not. There's no transaction. That's actually that's the trick.
Right, yeah, so it's not submitting a transaction.
There's no transaction, and since there's no transaction, it's faster. And you don't have to worry about nested transactions blowing things up. And we'll see why that's important for really evil, mutable, unsafe perform I/O code, which we're absolutely going to be covering today. So why do all of these operations need to live in I/O or live in STM? Every single one of them returns a value wrapped up. Why can't we have read IORef just return A? Why does it have to be an I/O of A?
It's doing a side effect.
What side effect is it performing? It's not launching missiles.
It's mutating variable.
Not read IORef.
The reference can change while you're not looking.
The reference can change. Yeah, you're right. We would violate referential transparency if read IORef could return a different result each time, referential transparency would be violated. Everything to do with mutable references in Haskell is ultimately going to return some kind of an action which can be performed and tell you the current state of the universe. All right, so exercise 2. We already have an IORef version of the code. Exercise 2 is simply going to take the IORef version and convert it over to TVAR. We'll take about 3 minutes on this one. Yeah.
Put up definitions again.
Yeah. In fact, I can't get it all on the screen at the same time. Oh, fine. I'll just go back over there. If you didn't complete it yet, don't worry, but we're going to jump over and start playing around with a solution. So again, we'll follow the same thing as last time. I'll start off by trying to run this thing. So variable not in scope, write IORef and read IORef. What should I replace this write IORef and read IORef with? Is that enough to get this program to work? No. OK. Let's ask GHC why. Could it match type STM with IO? Could it match type STM with IO? Could it match type? I'm seeing a pattern here. Who knows what's going wrong? In the wrong monad. Which monad should I be in? How do I get this to happen? How do I fix this? Where do I put the atomically? Before? Up here?
Well, then puts you one problem.
Then what? What? Put Sterling isn't going to work. Put Sterling lives in I/O.
But I can have the whole do notation be a private method that just returns a STM, and then I can bind to it.
From what point? Well, actually, first, just to address the OCD on my part, let's see it. OK, so now things are reversed. Previously, it was saying, could I match type STM with IO? Now it's, could I match type IO with STM? It expected STM, and now it got an IO. Because this put Sterling performs an IO action. For some reason, we can't interact with the outside world inside of STM. We'll see why that would be a really bad idea in a second, once we understand how rollbacks and retries work. Let's not worry about that. At this point, let's simply try to address the compiler. So Pavel has one idea. Why don't we just create a do block? Does someone have a different idea? Even if you don't believe that's the right way to solve it, give me a different idea. Yeah?
Outside the blocking by compose it atomically.
OK, I think that's the same thing he was saying. I want to. That's basically the right answer. I don't want the right answer right now. I want a different answer first.
I guess every line could be atomically. Right. I really want to do that.
I really, really want to do that.
But then,
no, I really.
But nothing works in transaction anymore, right?
One sec. I'm going to want you to say that. This works. But there's a problem with it. Who knows what the problem is? What's the problem?
Well, each line is executing a transaction and finishes the transaction.
Very good.
IORef again.
It's exactly like IORef. We've gone all the way back. Atomically creates a transaction. Each one of these lines is its own transaction. Everything is fine with the way that this code is written right now. But we're not at all taking advantage of STM the way it's happening here. Instead, we can do something like this. I'm just making sure it actually, no, of course it doesn't. There we go. So instead, we put all of our interactions with this variable, with these variables, inside this atomically call. Everything happens in a single transaction. We don't have to worry about any other thread potentially disrupting things. Yeah?
So just a question on this. If you don't pass in the TM-var here...
T-var. This is a T-var, by the way.
Sorry, T-var here. Is there any way to get it outside of that block? Because like right now, you can't do anything with this.
Right now, this is crappy code, and it means nothing. Correct. There's no way that, oh, can you pass the variable outside? The answer is yes.
Okay, you can get that. Okay.
You can do that. Ignore the fact that it says var and val, and those look really similar. But yeah, you can do that. And that's a great question. That is, essentially, there's no point in using STM if the variables all stay within the same transaction. Yep. Yes, absolutely.
Well, and originally you showed new T-var-IO.
Ah, so
Yeah,
new.
so you could have created that outside of the block.
Ooh.
This is how I did it, was new T-var-IO outside the block, and then just use it inside.
This,
Try to reach it after.
and this would be another way of doing things. This one doesn't feel as bad as the previous step of doing a whole bunch of different atomicallys. We created the variable, but then all of our interactions, our subsequent interactions with the variable, happen atomically. That's pretty good.
Should we infer it to mean that it's not as good as creating a T-var inside the transaction?
No, you don't have to infer that. We'll see examples both ways. All right, so what exactly does atomically mean? I've told you it's a transaction, it's running things. We can look at the type level and see it's converting STM to IO. More accurately, it's running an STM action in IO. But what exactly is it performing? Within the single call to atomically, all changes to all variables that are referenced either all commit simultaneously or none of them commit at all. A block succeeds, or all the changes that you tried out are rolled back. It's not too terribly important to worry about how this is dealt with by GHC's runtime system. It's using a transaction log. Not important for our purposes, and I'm not an expert on it anyway, so I'll just look like an idiot. I'm not going to say anything. We're going to jump right over to the next exercise and see the previous approach that we were taking of atomically on each line. We couldn't see a problem with it before, but now we're going to see a problem with it, and now we want to solve it.
What is race underscore doing?
Oh, yes, sorry. So down here, the main function, which you're not going to be modifying, is running a test suite. This race, wait, there's no race on.
Oh, wait, the number, oh, I'm on 1.4, sorry.
Yeah. Replicate concurrently 100,000 is running 100,000 copies at once of this action.
I see that having to do with saying that unrecognized GHC flag.
Well, I can't see async, even though I definitely have it installed.
Hold on.
I think the GHCR equals threaded. So,
Which version of stack do you have?
Oh, because
Oh, wait.
stacks 1.9.1.
I'm on head, I think.
Oh, well, I'm also on head. So that's not going to solve it. If you're having trouble with that, do stack run GHC instead and do a stack build of async first. Sorry, say again.
it's stack run GHC. I'm like running this
You're running what?
93.
Sorry, no, not the 193. I was trying something out myself. You can do something like this. We have what?
About half a blockchain here.
The blockchain. I'm just not understanding what.
Oh, no, it's like, I'm just joking. It's like, oh, look, we're like atomically.
Oh.
That counts like a half blockchain.
See, blockchains aren't important. We just needed global STM and everything would have been fine. Second. What's
I'm getting issues with the run HC. It says HSpec.
do -- package HSpec. Yeah. This may be the only exercise that has these problems because it has the more complex line at the top. Yeah. The people who are having trouble with this, you didn't have, Colin, you didn't have trouble with the previous exercise, did you?
No.
Okay.
But I did notice that the flag at the top.
Right. Okay, so let's just do this one together and then hopefully the problems won't exist for the following ones. Let me demonstrate what the issue is. Expected 0, but got 15. We're sending money from one account to another. The way that this works is you read the value out of the one account, you write back a deducted value, you read the value out of the second account, you add an updated value. But if two threads are reading and writing at the same time, you end up with a race condition. Right now, each one of these reads and writes is occurring in its own transaction. So instead, how do we want to solve this? One transaction. What do we do to change it? Knock off all these atomicallys. Boom. Right? Boom. Yes. No? No, it's because I saved the wrong file. There we go. Who here has ever tried to solve this problem in another language? Someone tell me some idea of how you would solve this problem in a different language that didn't have STM. Mutexes. Which order would you lock the variables in? The same order. What do you mean the same order? You mean the sender and then the receiver?
You have to stay the same both times, right? Both threads are in the same order.
You have to have some kind of absolute ordering of all of the individual mutexes. Make sure that you're not screwing that up. Otherwise, you run into a deadlock. That's not a lot of fun. This is a lot of fun. I like this. So now a question. What happens if one thread reads this TVAR, it keeps going, and another thread writes that TVAR?
The reader thread fails, basically, rolls back and tries again.
Did everyone hear that? I'll say it again for the recording anyway. The first thread, the one that did the reading only, is going to notice that another thread updated a variable that it was looking at. It's going to throw away all of the actions that it performed, all of the changes to variables, and it's going to retry. It's going to start the whole thing over again, throwing away any kind of modifications that it made, and now getting updated to the current state of the world with other variables. Yeah?
So let's say you've got two threads running. One is trying to construct a large transaction, and the other just over and over making little twiddly changes.
Yeah.
This is one of the variables in here. Is he just going to keep running and basically trolling this guy who gets halfway through the transaction over and over and over?
It's an advanced question, but yes, STM is subject to a live lock. You could run into a situation where a large complex transaction is getting blocked by smaller transactions. I haven't seen that pop up very much. I've heard reports of it, but I don't think I've actually seen it occur myself. If you put in a lot of very complicated logic in your transactions, you could run into that. Typically speaking, we try to avoid that. And many of the more, the larger runtime things like performing I/O, you can't do inside of an STM transaction anyway.
Right.
So it prevents.
That's why there's no I/O to STM, because there would be a rollback.
Yes. So why can't we print a message to the screen inside of our STM transaction? Say again? We can't unprint it. You can't do anything inside a transaction that can't be undone. If you print to the screen, and then you do a rollback, and you retry, you're going to just keep printing a message multiple times, which you don't want to do. The limitation of STM is everything inside of it must be pure. It so happens we're using a programming language which is really good at pure code. So that's kind of nice. And if I'm not mistaken, STM was a weekend project for GHC, which is kind of cool. OK, any questions about this exercise?
Was STM first thought out in Haskell, or was it known before?
Was STM first invented in Haskell? I think it may have been, but I'm not sure. It was Clojure first? OK. I'm not a historian. Can we use? Yes. There is. I did this just to demonstrate the bug. But yes, there's also a modify tvar. So instead of this reading and then writing, what you could do is you could do modify tvar from minus amount. Actually, sorry, subtract. Anyone who knows why you have to type in subtract, I feel sorry for you also. You do that, and then if anyone really wants to get into laziness issues, you want to do modify prime. Yes?
Elaborate on that?
On which part?
Why do you need prime versus not?
If you don't put on the prime, then what you're actually going to end up writing to the variable is a thunk, which doesn't leave things evaluated. The thunk representation of this is more expensive to allocate and hold on to than simply performing addition or subtraction.
But if you had a complex, if you had an operation that was not true, and you weren't sure how the Trojan ever pick it up, does it make sense to leave the thunk in place?
If you have something very complex, that's going to take a lot of CPU time, or may never be run, then yeah, you can write a thunk. And in fact, getting back to the idea of a live lock, you can in fact bypass some of the live lock issues by writing a thunk and then forcing the thunk from outside of the STM transaction. That's a possibility. If that didn't make sense, don't worry. It's a much more advanced topic and not something we're really going to be covering today. OK. So in this exercise, we had multiple threads operating on the same. Yeah, so we've explained this data race. Do people have questions about this kind of a data race? No. OK. So the important words from everything I've been telling you and the important part for the atomically function are rollback, retry, and commit. When you run a transaction, it attempts to commit the changes it made. If it succeeds at committing those changes, everything is done. If it fails because some other thread modified those variables in the interim, it rolls back the changes locally, and then it retries everything again. OK. Yeah. There is no limit to the number of times it's going to retry. So you might be wondering, is this just going to be like some kind of spinning your CPU up to, that's the implied question, right? So how does GHC decide that it's time to retry a transaction? In the example that we just saw, it can retry immediately. Because all we have to do is we have to look at the new version of the data and try again. But that's not always going to be the case. And I'll explain other ways that GHC is able to schedule this. All right. Everything we saw so far was an implicit retry. There's no part in our code where we told GHC to retry. It figured it out for us. However, we could also explicitly decide that a retry of the transaction is necessary, such as, for example, if some condition doesn't hold. So we're going to implement another one of my and this is actually one of my favorite examples. I use it all the time talking about bank accounts. Alice is going to be receiving a paycheck on a regular basis. I think I put it at 1 second. I would love to receive $5 every second. That would be awesome. But Alice is going to receive her paycheck, and then when she has enough money, she's going to transfer a lump sum payment to Bob. So go ahead and pop open exercise 4. The tasks in this one we're going to get 5 minutes for. Make it compile, add a call to the retry function to prevent the balance from becoming negative, and then fix a race condition. And if you have extra time and you want to, you can try using the check function. No, there isn't. If you want to, you could add a stack YAML and get that running, but no. Oh, I think you could use your OS's like iNotify command line tools if you wanted. I don't think so, but you could. The fact is, we're not using any kind of special features. You could use any snapshot, and these are good. Okay. Again, don't worry if you didn't get through the whole exercise, but we're going to move on and solve it together. Firstly, did anyone figure out what the race condition is? What is it? Reading and writing in 2 separate transactions. How should we do it? Atomically. You may notice a theme that I'm trying to get across here. Notice that the thread delay is not inside the transaction. 2 reasons for that. 1, it won't compile. That's always a good reason for not doing something. However, there's another reason. Even if you could put a thread delay, which actually could happen inside STM, the problem is you would never want to do that. You don't want to make a transaction take long for no reason. Do it outside of the transaction. We'll see that there's something called register delay, which if you really need something to be time sensitive inside STM, you can do that. There's an example of that later. Okay, so that was the race condition. This code does not compile still. Actually, we're not going to cheat. We're not going to ask GHC. Who knows why the code doesn't compile?
Because that's not inside of a transaction.
It's not inside a transaction. Where should we put the transaction?
Right after the let.
Right here? You could. We can do it right here at the top. The let can stay inside. There's a great reason for this, because I don't feel like reformatting all the code, because I'm lazy. Semantically, they're exactly the same thing. But this is nicer, because I'm lazy. Haskellers are allowed to be lazy. It's fine. It's a virtue. OK. Finally, the retry call. Where does the retry call go? So if Alice Arig is greater than or equal to amount, means Alice has enough money to make this payment. If that's the case, everything is fine. Otherwise, retry. At that point, you're saying to the runtime system, this doesn't work. I can't do this. Try again later. It's not your responsibility to figure out when later is. It will figure it out for you. We'll talk about that in a second. If all of this works, then we're able to go ahead and make these changes, these transactions. a little kind of cool thing. This would also work. You can move it around. Here, we've made the changes first, and then we check the condition. Well, actually, you'd have to, oh no, that's fine. Then you'd have to make the changes. This isn't as good because now you actually perform more changes in your log before you do your checking. So you may as well get the checking out of the way earlier. And I also think just mentally, this looks like saner code. Another thing we could do is use the check function. Did anyone figure out how to use check in this case? What should I do? These two things are absolutely identical. It's cool, it's nice, it's convenient. Check, I think, in my opinion, this is much more explicit about what's going on. So I think it's prettier code, easier code. Yeah?
So originally when I did this, I didn't realize that retry or check were actually functions at all. So I tried to do this recursively.
OK.
So what happens when you have recursively nested transactions?
You mean you call it atomically inside atomically?
I actually didn't call it atomically. I had my STM block called itself.
Right. So if you do that, what you're going to do is you're creating an infinite loop. Because the variables are never going to change. Not exactly true. I actually have to check with the runtime system. It may notice that, that something else changed it. You are going to create something that's going to spin for a long time.
It actually worked, but so it didn't not run, and it didn't transfer 40, but I really, yeah.
Check the CPU while you're doing it. That would be very interesting. All right.
It probably worked as a race.
It's the other so what ended up happening was another thread. The other thread updated the TVAR, and then this transaction got interrupted.
I just only have a question. What is this race function?
Yeah.
What is this?
Race says run two things in two separate threads and stop when one of them is done.
This belongs to which package?
The async package. And the async package is awesome and really cool, and you should use it.
Is it better, in this case, so you're going to read two independent T-bars that are, in this case at least, kind of intertwined. Is it better to read those, I mean, not a race image or anything, but is it better to read those as a single transaction, read both? Or is it better to keep each individual transaction smaller, just read one bar?
In this case, we absolutely want to deal with both variables in the same transaction. We don't want to end up in any kind of a situation where some other thread may be able to update one of the variables separately. Now, you might be able to reason your way out of it in this kind of a case and say, well, no, I actually made sure that this thing is all going to work correctly. But what happens if an asynchronous exception happens or something goes wrong? As much as possible, throw everything into a single transaction. If you run into some kind of performance problem, which in my experience, this isn't where the performance problems are, then you could worry about figuring out other ways around it. But I would absolutely recommend large transactions as much as possible, simple as possible. Yeah?
So the race condition here is that some of Alice's pay would get lost. So should we be checking at the end, rather than just letting it run infinitely, should we be doing replicate n some number of times that she gets paid, and then check at the end that she's been paid the right amount?
Are you asking to make sure to check that the code is correct, or are you saying that the code won't be correct unless you do that?
I'm saying for the purpose of this example, it would be helpful to add that because it may be possible to brute force it somehow and get them
We're not.
paid.
We could add a test. This isn't a test. Right now, this is just a runner to see what's going on. But there's no test in here to prove that things are working correctly. Yeah?
If you're familiar with the rules around database transactions, what the boundaries of it should be, are those any different for STM, or do the rules translate?
They translate pretty well. One of the big differences around database transactions, to some extent, database transactions don't get the same kind of rollback, depending on databases, depending on lots of different things. So the semantics are a little bit different, but for the most part, you could follow the same idea. You also don't have a distributed systems issue in STM like you do with database transactions, which is nice. OK. Here's the million-dollar question. We retry. When do we retry? Immediately is one option, and it's a fair option. Other ideas?
We could do some kind of sleeper method. Either like constant or exponential backoff.
Constant or exponential backoff, another option.
With a variable change.
Oh.
STM is really smart. As you are going through a transaction, it's going to keep track of what it is that you are looking at. And because everything is pure, the only thing that can affect your transaction are the variables that you've already read. So if you run through this transaction and you hit a retry, the runtime system knows it will force a retry again. It will fail again until one of those variables changes. So it's able to go to sleep, and the runtime system will wake up the thread automatically the first time there's a chance that the transaction will succeed. Now, you're not guaranteed that the transaction will succeed next time, but it does avoid any kind of a spin lock kind of condition occurring.
So that's why retry doesn't hook your CPU.
Retry does not hook your CPU, exactly. Retry is really nice. It provides blocking without any kind of explicit thought. That's actually an important term here. It is a blocking activity. OK. Questions about this exercise? Could you speak up a bit? Correct. Each of these things are separate transactions, and they're separate threads. You're not able to have a transaction that spans separate threads. So yes, this is one transaction. Down here is another. OK. I was told that we're going to have a break. Is 2 o'clock the right time for the break? Do we wait a little longer?
Whatever you want.
OK, so how's this? I'll introduce everyone to the next exercise, and then we'll take a break so that you can think about it. I can nerd snipe all of you appropriately. OK.
There is a longer break at 3.
Oh, well, oh, so the break is at 3. We're just running through until 3? Yeah. Oh, OK. Got it. OK. So we're not taking a break now. All right. Onward. You guys are my prisoners, I guess, for another hour.
Oh, really?
OK. So you can explicitly use the retry or check to trigger a retry of the transaction. Before, we saw an implicit way of retrying a transaction. The implicit way, who remembers what was the implicit way of causing a retry to occur? Say again? If another thread modifies a variable that you were looking at, a retry automatically happens. In addition to that, you can manually cause a retry to happen by calling retry or a function that calls retry. Yeah?
So if your check line is the first thing in your STM block,
yeah.
is it going to kind of scan past that to see which variables to monitor?
No. It's not lexical in any way. It's going to look at what happened previously. You have to have read. OK, so for example, so if you did this, this thing is a deadlock. This thing will never succeed. This is saying always retry. Doesn't matter what's coming after it.
What if you put line 36 above and it fails that check immediately?
Well, it can't. This won't even compile, because you have to read a variable first.
Sorry, slightly off-topic question. The forever, why does that keep the program running forever?
Oh, that's a good question. Why does forever not actually keep it running forever? Because the race down here says whenever one of the threads completes, then it's going to be done.
That's all in async, right?
Say again?
That's all in async?
That's all in the async package.
It does that by an asynchronous exception?
Correct.
I'm trying to just confirm something quickly. Can you put a retry at the beginning there? We just want to see if GHC will detect it. Or if it will.
OK, anyone want to take bets on what's going to happen? I have a guess. My guess is that we're going to get blocked indefinitely on STM. Wait, oh, sorry. It would help if I ran the right code. We're all waiting. Yeah. It'll run indefinitely. I'm actually surprised. I thought GHC would have generated an exception in that case. I guess they decided none of us were ever going to be dumb enough to just call retry right at the beginning.
Because there's no variables, so it doesn't, like, it is looking at a variable and constantly trying. So
Yep. They're,
And then what's happening right now, the other thread in that forever is continuously running.
yeah, it's like going to sleep without setting an alarm clock or not having any kids. Nothing's going to wake you up. Okay.
I'm sending that to Marion, Michael.
Thank you. Okay, so since the only side effects allowed in a transaction are those that interact with TVARs, we know that retrying a transaction beforehand, that retrying a transaction when a variable hasn't been modified is going to be useless. Can someone here come up with a way that that claim is false? Say again? What? So the claim is GHC knows when it needs to retry a transaction. It knows that because it knows that everything will run the same way unless one of the TVARs changes. That's not a 100% true claim. Yeah?
What if you write the same value to the TVAR that's already in it? Like,
Well, if you,
change the value in it, but it's still.
I think you're proving the contrapositive or something along those lines. In that case, you may get woken up unnecessarily, but then you'll just end up blocking again. I'm saying the other way around. Is there some way that retrying without the variables changing could cause your program to succeed when it previously retried? Yes, thank you. If you do unsafe perform IO and you read a file or you read something else, yes, you can actually violate some of these rules. Moral of the story is you really don't want to mix unsafe perform IO with STM. Other moral of the story is you don't want to use unsafe perform IO ever if you can avoid it. I will still show you guys a time to use unsafe perform IO, so don't worry. All right, who here has ever heard of an MVAR? MVARs are mutex variables in Haskell. These things live in IO, and they're like IO refs, except they can be empty or full, and you can block on them. TMVARs are like MVARs, except they work in STM. And a fun exercise that we're not going to do now, if you wanted to, is implement your own TMVAR on top of TVARs. Completely doable, and if you get stuck trying to implement that yourself, you can just go look at the STM library and see how it's implemented. All right. So TMVARs are this fusion of things we are going, oh, I was wrong. We are going to implement them. Sorry, I got that backwards. Yes, we're going to go implement TMVARs right now.
Surprise!
Surprise me. And we're going to do 5 minutes on this one. All right, we're going to go ahead and start implementing this together. First thing we're going to do is make it compile, because right now we get an error message about an occurs check, cannot construct the infinite type, blah, blah, blah. Anyone know how to fix this error? Just A. A TVAR is never empty. A TVAR always has some kind of a value in it. But a TMVAR needs to be emptyable. Therefore, the representation of a TMVAR is a TVAR with a maybe value inside of it. And therefore, if you want to actually put something into the TMVAR, you have to wrap it with just. And now we get errors. So these are test errors, not compilation errors. Error call. Do something with this. All right. Let's start off with this take TMVAR implementation. Take TMVAR has the idea that if there's a TMVAR and there's a value in it, you want to take it out, meaning actually pull it out and empty out the TMVAR. We do the emptying out here. We write nothing into the variable. What is it that we want to do here? Pure. STM is an applicative, and it's a monad, and therefore pure works just fine. Let's see if we solve our first error. And we did. We have one less failure. Test-driven development works. Yay. OK. So next one. Try put TMVAR is also failing because of an undefined call. So let's try to figure this one out. Try put TMVAR will take a value and put it into a TMVAR if it's empty. And if it's empty, then it will succeed. Sorry, if it was able to put it in, it's going to return true. If there's already a value sitting in this TMVAR, it's going to return false. So what do we want to do in these two cases? We have a nothing case and a just case. What should we be returning in the nothing case? pure true. And down here, pure false. Cool. Down to one problem. This one is a little trickier. Try take tm var should return nothing in this case, but it's not. So why is that? Let's look at the implementation of try take tm var. Make sure the var is empty after this. You'll need to add something here. OK, it was nice of whoever wrote this file to tell us where we needed to make some changes. No, I'm thinking myself, to be honest. I wouldn't have remembered. OK, what goes on here? What do we need to put in here? Not a case. Nice try? No. Actually, we could do a case. We'll do the case version next, and you'll see why it's not necessary. Say again? Bingo. And that's it. We now have an implementation of TM vars. So you guys can all go open up a pull request after this is done to the STM package and tell them you want to use your implementation instead of the one they've got. I'm sure they'll be very happy to receive 50 or so pull requests in 10 minutes. OK, the reason we don't need the case here. We could do a case expression, case x of just, just y, and then we would do, and then pure just y, and nothing would be pure nothing. That's what we could do. The reason we don't need to do that is if we just write to the tvar nothing when there's already a nothing there, it'll do the same thing. Might get into some kind of performance issues where this is actually a better version of the code, but not strictly necessary. OK. Questions about implementing tm var?
There's some errors up top.
Oh, you're right. There were. That's right. I forgot about those. What should we do here? If we try to take a tm var and there's nothing there, what should we do? Yeah, I screwed up the test suite. That should have been caught by the test suite. My mistake. So now that we've got a retry going on there, what is going to happen at runtime if a tm var is empty? Block until it changes. This is usually exactly what you're looking for if you're reaching for a tm var. That's the kind of behavior you'd want. If that's not the behavior you wanted, you probably wanted a tvar anyway. OK? And put tm var, what is the thing that we should do if it's already full when we try to put? Also retry. Good. Anything else in this that I forgot to test? OK. Cool. So there was a little bit of duplication in the way that we ended up writing that right now. We had a try put tm var and a put tm var, a try take tm var and a take tm var. It would be nice if we could reduce some of that code duplication. And that's where we're going to come up with the alternative instance. So for those who don't know, alternative is a type class. It's a child class of applicative. And it provides the ability to say, first try doing this action, and then try doing this action. And there are other interpretations of the type class, but that's the one we're going to do here. We're going to use here. In the context of STM, when you use alternative, what you're actually saying is, I've got two different actions I may want to perform inside the transaction. Try the first one. If the first one retries, treat that as a failure, roll back all the changes that action performed, and then try this other thing. And this allows us to have some kind of a fallback if something doesn't work the way we wanted it to. The operator that we use for this is this angle pipe thing, which you can think of as OR. Do this or do that. Those of you who have ever seen it, there's also an or else function in the STM package, which is exactly the same thing as this. I prefer the operator version. So for anyone who's familiar with the alternative laws, there's also an empty method inside alternative. Who can guess what the meaning of empty is in the context of STM? Retry. I'm really impressed. OK. Yes? As it happens, empty is exactly the same as retry, so you can get rid of the retry function and just throw empty in everywhere and everything is fine. Please don't do that. Retry is really a nice name. All right, the nice thing about this alternative, you can build up much, much more complex concepts based off of simpler things. And in order to do that, we're going to use exercise 6. Exercise 6 is going to build exercise 5 in a different way. So let's go ahead and jump over there. So out of curiosity, anyone solve either one of the implementations?
Right now you're using the TM part from the library, right?
Correct.
And what's the data constructor for it?
You don't have access to it.
I don't have access.
You don't have access to the data constructor. You have to do this opaquely. You have to use the public API.
STM is on it, by the way.
OK, so let's work on this together. I'm only going to give you guys the first answer together. And the second solution you'll be able to work on later. So try take TMVAR. Before we jump into the solution, what function from STM do you think we're going to use in order to try to implement this ourselves? Take TMVAR. So let's just do the dumbest thing I can possibly think of and throw that on the screen. Is that going to compile? First question. Why isn't it going to compile? It's not a maybe. So let's just forget about semantics. Let's just see if we can get this thing to compile. So this is going to be an A. What do I do in order to get this thing to compile? Pure just A. So I'm going to throw in an undefined here instead. Well, that's not doing anything. It's blocked. So the point is it did compile, but we have some kind of a block. Why do we have a block here? What's going on? We also only have this just case. Doesn't it seem like we may want to have a nothing return value if we're returning a maybe value? So let's think about this a little bit more semantically now. The TMVAR has two possible states that it could be in, full or empty. Which case are we dealing with here? The full case. And if the thing is empty, what's going to happen in the current version of the code? It's going, say? It's going to? It's going to block. It's going to retry. It's not going to end. It's going to retry. If code is retrying and we want to try to do something else, what is it that we want to slap on there? Either the thing is full and therefore return it in a just, or the thing is empty and then what do we want to do? Here, another way of looking at this, which is a little bit easier. Full or not full.
Oh, okay. Would you not want to just use that command?
We could. I'm not. It's easier to see the code this way. For anyone who's curious, those two lines of code are those two implementations of full are identical. OK, so homework for everyone else to do. Try put TMVAR as well. I refuse to give you guys the solution and forget about the fact that I have solution.hs in the same directory. Yeah. No. Sort of. OK, alternative is one of the more powerful concepts in STM. In fact, you've learned all the most powerful concepts of STM at this point. The ability to retry, the ability to have transactions, and the ability to fall back and try a different way of approaching things. Everything else is just commentary at this point. So channels / queues / FIFOs. T-chains and T-queues are two very common data structures used in STM. They both provide a FIFO queue of items. Values come in, values come out, first in, first out. T-chan is a little bit more powerful than a T-queue. A T-chan allows you to create something called a broadcast channel where you can have multiple readers from a single writer. I actually cannot think of a single time in my Haskell career that I've used a T-chan. I think I've always used a T-queue. So don't feel like you're missing out on something if you don't have the use case for it right now. You may never have a use case for it. Could also be that there are lots of use cases and I just never ran into them myself. That's also a possibility. Both T-chan and T-queue are built into the STM package itself. There's an additional package called STM chans that provides a whole bunch of variants on queues and channels that you may want to play with as well. You could have a closable channel. So a closable channel would mean that the next time someone tries to read from it, they get told, no, this thing is already closed. And this can be a great way to implement worker threads. You know, a pool of worker threads that are all pulling off of a queue. In STM chans, I'll just show you the nomenclature a little bit. These are all the different names. So there's T for transactional. There's B for bounded, which we're about to see. M means closable. I think M means closable, right? That makes perfect sense. Anyone know why M can be used for closable? I think they're borrowing it from mvars. So mvars are mutexes that can be emptied. So of course, an emptyable, meaning closable. I think it's bad naming, but it doesn't matter. We're going to use it. We're going to use it, and we're going to like it. And then there's bounded, and then there's chan versus queue. So you go ahead and you do a combinatoric buildup. And of course, there are 8 different FIFO structures you may or may not want to use. TBMQ is probably the nicest one of these for general usage. I usually find that I want to be able to close a channel at some point. I usually find that the channel I want is actually a queue. I usually find that bounding is good for putting back pressure on things. All that said, there's nothing wrong with using any of these depending on the use case that you've got. Combining bounded closable queues with the async library and going ahead and being able to fork off 8 threads all doing the same thing at the same time, you can build up really complex and really nice abstractions very easily. Yeah?
Is the difference between channel and queue the sort of multiple reader versus single reader?
Yes. Channels have the ability to have a multiple reader concept. And that, I believe that's the only difference between these things. OK, let's go ahead and jump over to exercise 7 to try this part out. And since we're using a TBM queue, I'm going to put the documentation that's relevant to a TBM queue on the screen up here. Yeah.
If you have your fail case or bracket your success case, that's going to screw things up, right?
That's going to?
It's going to mean that the fail case always, oh, well, OK, I'll just do this, and that worked.
Right.
So it's never going to try to do the thing that you want to do, correct?
I think you're saying I think what you're saying is the other way around. So yeah, let's pull up the code.
So if you had not full or pipe full.
Yeah. Oh, that is what, OK, so I misunderstood you. Yeah, if you do it in that order, not full is always going to succeed. Right. You're always going to return nothing, and you're never going to actually perform the thing. Yes. Right, okay. Yes. I should have pointed that out. That's a very good catch.
The test caught it, though, so OK.
Yay, tests. OK. All right, I had code on the screen.
Semantics of the worker to do atomically per thing pulled off or atomically.
What do you think I want? What do you think is reasonable? Say again?
Former seems more sane.
That you would do you would do one work item at a time. Why is that more sane?
Because you don't draining the queue.
The alternative is you'd have to drain the entire queue and then perform all of them at once. So yes, you're going to pull one off at a time. Okay, let's go ahead and work on this one together. Let's see. We'll start off by running this and seeing where it fails. So the first thing is we've got some type errors on line 12 and 17. So in this body. Who here sees what the problem is? Problems. Quite a few things, in fact. Yeah.
One of them is that it will just loop forever.
It will loop forever. That does seem like a little bit of a problem. Probably don't want that. Okay. What should be the stopping condition?
Nothing.
Nothing, what do you mean by?
Nothing pays from reading from the queue.
Yeah, TPM can give you
Since this is a closable queue, when you read off of it, you can either get the next value in the queue, or you can get a nothing telling you that there's nothing else there. What about the other case? What if the queue isn't closed, but there's nothing left on the queue? What? There you would wait. So we actually have 3 different possibilities of what could happen, but as far as the types are concerned, there are only 2 of them that we care about. So the result, we'll now call it an MA. Case MA of. So what do we want to do in the nothing case?
That's an empty.
Say again?
That's in a monad, right? MA.
What do you mean it's in a monad? Oh, sorry, I'm saying maybe A.
Yeah, but it's in the STM monad.
Yes?
So you can't just case MA right there.
That's right. The result isn't in a monad anymore. I already bound.
the left arrow already.
I binded it.
Okay.
I bounded it out. So what do we want to do in the case of nothing?
Return. Well, pure.
Cool. We want to get out. We're done. All right, what do we want to do in the just A case? That's actually it. So we try to read something off of the queue. If the queue is empty and all done and closed, then we're done. Otherwise, we perform the action on the next thing in the queue, and we loop again. Is this code now working?
No.
What's wrong? We're in I/O. It needs to be atomically. Both correct answers. Where does the atomically go? Where? In front. The read? Did someone say read?
Yeah.
I've always told you guys to put it in front of the do. Why aren't you putting it in front of the do this time? The action has to be in I/O. So in this case, despite all the things that I've been hinting at previously, here we are really going to have this really tiny transaction in this case, because that's the only thing that is actually looking at the STM stuff in this place. Yes, that's correct. If I'm not mistaken, that is the only change to this function which is necessary. It changes, I should say. Let's see if this thing compiles. Well, it compiles, but we get the wrong result. So let's look through the rest of the code. Well, someone politely told us that this wasn't right. Filler. Who can guess what filler is supposed to do? Fill the queue, populate the queue. Is pure unit populating the queue? No, it is not. Okay, so what do we do? Traverse the inputs. I'll use I think mapm might be the most recognized function name. Okay, so mapm something inputs. Say again?
Write TBMQ.
Write TBMQ Q. Are we done? We need atomically in here. Where do we need atomically? In front of the right. Say that again for everyone.
Or else you have to wait for all the writes to finish. And then there's no point. You'll have nothing here.
Let's go ahead and run. I'm doing the opposite. This is the bad one. Let's run it first. We'll get to why it didn't. Well, actually, this is blocked. Here's what's happening. Atomically is running on the entire block, on this entire transaction. This transaction is going to write all of the inputs into this queue. What is this? It's a bounded queue. What's the size of the queue? It's 16. How many things are in that list? 1,000. So it tries to write all of them. It fails, so it calls a retry, because that's what it does. And then it sits around and it waits for somebody to do something. But there's nobody around to help us, and no one ever could figure out a way to make a 16-size queue hold 1,000 values. So we do that. This may be a little bit easier to read. I'm not sure. I find it a little easier to read, perhaps. Cool. Personally, I think as far as a pulled work stealing mechanism, that's a pretty short example of code. Are there any questions people want to ask about it?
Yeah, sorry, I just got very lost. What is yanking stuff off the queue while this is being built?
The workers, so there are, sorry, let me start off from over here. We have a bunch of workers. The workers are all reading off of the queue. That's the function we wrote in the first place, which is calling read TBMQ. That's going to pull things off of the beginning of the queue. At the same time, concurrently with that, our filler is going to sit on the other end and keep slamming things onto the back of the queue. So we've got this little dance of 8 threads pulling, 1 thread filling. If it gets to a point where the queue is completely full, the filler is going to block. If it gets to a point where the queue is empty, but the filler is still running, so it hasn't closed things out yet, the workers are going to block and wait for more things to become available. Yeah?
Is the queue, where we have the closed TBM queue, is that retry if there's still things on the queue?
What closed TBMQ, if I remember correctly, and I could be mistaken about this, I think closed TBMQ always succeeds immediately, and it sets a flag. If there are still things in the queue, then those things in the queue get read off. And then once the queue is empty, then the next thing is going to be nothing. Also, if you try to write to the queue after it's been closed, it generates an exception.
Okay, so yes,
I think so.
There's no issue here with you close it before you consume everything.
No, you don't. You're correct. There's no issue there. Okay, I know everyone is probably intimidated about the fact that we still have 4 exercises to get through or something like that. Don't worry, it's not as bad as it seems, and you'll see why in a second. All right.
Exercise 8 doesn't have a solution.
Exercise 8 only has a solution. That's correct. That's why you don't have to be so worried. We're actually past the hard part. Deadlocks. So now we've seen a few cases of deadlocks, of things blocking indefinitely. And a few people in here, I think myself included, have said blocked indefinitely on STM. What's going on? What are we talking about? STM really helps make race conditions less likely, but like I said at the beginning, they're not impossible. It is completely possible to create a race condition or create a deadlock with STM. Fake exercise 8 demonstrates this.
Hey,
There is no spoon. New tvar IO 5. We read the tvar. We check if it's greater than or equal to 10. And if that doesn't happen, it blocks forever. Let's go ahead and try running this thing. If we're lucky about this, we get that instead. What's really cool is GHC is able to leverage the garbage collector to know whether there are any other threads that are referencing a variable. If all threads that are referencing the tvar that we're blocked on are all in the blocked state, then GHC knows that there's a deadlock.
Is that a warning or?
That is an asynchronous exception which killed the thread. GHC's runtime system itself will throw this asynchronous exception. It is a wonderful piece of debugging help. It is much, much nicer to get an async exception than it is to get nothing at all and you don't know why.
Why didn't it blow up the first time?
So why didn't it blow up the first time? I repeat it for the...
It did for me eventually.
It did eventually. It's non-deterministic. All of this is based off of when the garbage collector runs, how it happens. You may have noticed I compiled it and ran it. Now it's using the single-threaded runtime instead of the multi-threaded runtime. It has optimization. All of these different things can cause things to happen. The takeaway is this is a really nice feature. Do not depend on this feature. This is a feature for convenience only. Some people in the Haskell ecosystem have tried to write libraries based on using this. You know, I'm going to catch that exception, and that's going to tell me something, and I'm going to change the way. No, 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 no. You do not depend on this. This is a last resort kind of thing to help you out. It is not something that you use to structure control flow, ever.
You would never write any kind of code that caught the asynchronous exception?
Outside of debugging code, you know, like maybe maybe instead of just going to the normal log system, I'll have an automated angry email sent to the devs saying you suck. I don't know, something like that. You know, abusive programming. But besides that, no.
Abuse-driven development.
I like this. ADD. That was funnier than I thought. OK. So again, the point is, if you're lucky, you'll get that exception. Otherwise, you won't. Also, asynchronous exceptions. If anyone knows anything about me in Haskell, you probably know I talk way too much about asynchronous exceptions. They're great and they're wonderful. So it's great here. We've already seen them being used multiple times in these exercises. But yeah, they're not perfect. There are also some really weird corner cases where you can have multiple threads that are all in the block state. They all get killed at the same time, and sometimes that leads to funny things, which once again leads to the point, do not write deadlocks in your code. You don't have an excuse for me saying that GHC will catch them for you. I will hunt you down. OK. So it says final exercise. It's actually, I added more exercises at 4:30 in the morning because I'm jet lagged. So it's actually the final required exercise. The other ones are for fun for later. For our final exercise, we're going to play with global variables. Everyone loves global mutable variables, correct? Now, remember that in order to create a variable in Haskell, a mutable variable in Haskell, you have to perform an action. So how can you perform an action globally? How can you perform it outside of a do block or outside of the main function? Unsafe perform IO. Yay. OK. Go ahead and jump over to exercise 9. Wait, was there any? Yes. Gets inlined. And what you end up doing is, in each one of these places, counter is replaced by unsafe perform IO, atomically new tvar 0. Meaning that each use site of the global variable is a separate variable. You don't have a global variable anymore. So I'm not advocating global variables, just to be clear. This is if you happen to be using it. this is what you need to know about it. Stick a no inline on it. I think I have one library that uses a global variable. You're all free to try to guess which one it's in. It's hiding. It's HTTP client TLS. OK. What's the problem with this code? Who saw it? You have atomically inside. You have an atomically inside an atomically. And therefore, atomically was nested. One of the rules about STM, you can't have nested transactions. I've never read the papers or read the code or heard the full explanation, but it's pretty easy to just intuitively guess that if you have transactions running inside transactions, your head is going to explode. Head exploding, by the way, is a technical term in GHC. You can go look it up.
Why is it not compile time?
Why is what?
Why, is this meant that GHC catch a compile time? Rather than
Yes. No, not at compile time. This is a runtime exception.
is there no way for it to check this?
No.
You just not say it. Well, yeah.
Right. So who can figure out the way to solve this? Say again? Wait. Oh, wait, hold on. I like it.
You like evaluate from control that exception. You can just evaluate on the counter before you use it.
That was a really, I did not expect anyone to come up with that solution.
Control that exception.
Thank you. What's going on there? Because that's complicated. More complicated than I wanted to get, but it's awesome, so we're going to do it. This whole thing, when the program starts, is a thunk. It's a piece of I/O, a piece of an action that is going to be run the first time that thunk is evaluated. Right now, or sorry, not right now. Without that line, the first time that thunk is evaluated is right here inside the atomically. But if you force evaluation of the value first, of the thunk first, then that I/O action is run up here and everything is fine. Good solution. Better. Bless you. OK, you're now banned from using evaluate or seek or anything else. How do you solve this problem? Yeah. Very good. Get rid of the inner atomically. That works, right? New tvar.io. Now you guys know why I introduced that earlier on. This is the other reason. So besides performance, creating a new tvar doesn't need to be transactional. There's no reason for it to be. Sometimes you want to run it inside of a transaction. There's no advantage to forcing it to be run inside the transaction. So you can perform it like this. GHC has no problem with it. And it works.
Why would you want to create a tvar inside a transaction?
Sometimes you want to do things like you have a map inside a tvar, and the map inside the tvar contains tvars, and you are going to dynamically fill it up with more tvars.
Okay.
You could do.
Sometimes I'm creating one, sometimes I'm modifying it. So
Yeah.
right.
Right. There are some really awesome things. STM just composes. That's the really great thing. You just keep building more and more stuff out of it. I would say that the most common case, though, is that you're using new tvar.io, that you're creating these things out of a transaction. OK, cool. So that was the last required exercise for this. I have 2 additional exercises, which we could either go through together right now, or I can just leave for everyone. I'm going to guess people want to play around with these themselves. Is that accurate? It seemed like a group that enjoyed working through the exercises. There are also some extra credit ideas down here. This is unusual for one of my workshops, but we're finished a few minutes early, so that's nice. Does anyone have any kind of questions or things they'd like to see? Yeah?
Can you stuff like anything you want into a tvar? Like, can you stuff a function into a tvar?
You can put any boxed value inside a tvar. So basically, yes. The reason I'm pointing out boxed value, one of the things you do with mutability in Haskell sometimes is unboxed mutable vectors, for example, which can be really fast. You can't do that. You can't work on an unboxed value inside of a tvar. Everything in a tvar has to be a boxed value. Yeah?
What's the difference between boxed and unboxed?
Boxed values are on the heap, and there is a pointer to them. And unboxed values, like an unboxed vector, ends up getting written as bytes to a contiguous byte array. So if you have, forgetting about all this STM stuff, if you have 1,000 ints that you need to hold on to, a non-box vector will typically be drastically faster than a box vector or a list. Yeah?
Quick question. You showed us why we should use STM.
Yeah.
Could you also tell like the war stories why we shouldn't use it? Like, are there any cases where that just is not like
The biggest example of why you shouldn't use STM, if you have something where you want to hold onto a lock and perform I/O while you're holding the lock, it's much more difficult to do that with STM. You have to pull out bracket. You have to be very careful about exceptions and all these other things. Just use an mvar at that point. There are cases where you have such a simple requirement that an I/O ref is sufficient, and just go for that. But my default recommendation in all cases is start off with STM. When you know that you don't need STM or that STM isn't cutting the bill, then go ahead and switch over to something else. But STM as the default is absolutely what I recommend for mutable variables. Cool. Any other questions? OK. I'll be on the LambdaConf Slack if people want to ping me and discuss exercise solutions to this. So that was fun. Anyway, thank you very much, everyone.